with Ohm's Law. So we're going to start with Ohm's Law. So any ideas what is Ohm's Law? Okay, so
No.
all right. So Ohm's Law, or the person who's actually trying to find this law, is trying to find what this is telling us that if I increase the voltage of the circuit, the current through the circuit increases. So there is a direct relationship between voltage and current, right? Previously what we've discussed is that the current itself is the number of electrons, and voltage itself is the energy of the electron. So Ohm found out that if you give more energy to the electron, that is the voltage of course, the speed and the quantity of electrons eventually constituting to the current itself also increases through the circuit. Now this logic or this idea only holds true if, when we are testing this, something remains constant in the circuit. That something is a physical quantity, and in terms of mathematics we wanted something as a constant of proportionality. In our case, that constant is the resistance of that conductor. So this equation comes out as V equals to IR. So R is the resistance of that electronic component. Now, what do we mean by resistance? Simply put, that it is the hindrance or the opposition provided by the material itself to the flow of electrons. It can provide this opposition by not giving any electrons in the first place, just like insulators. So we will say that insulators have a very high resistance because they don't want electrons to flow through them. They don't like it, right? And we can also confirm this from another perspective, that it's possible that in some substances or some materials we do have electrons that will help the conduction of electricity, but due to the atomic structure of that material, the electrons will not be able to move or squeeze through that atomic structure rather easily. So even in that case, the hindrance will eventually become the resistance of that material, right? So resistance, if this remains constant, only then we can say that voltage and current are going to become proportional, or can be considered to be proportional. Now let's talk about resistance a bit more. And of course, since they are directly proportional, we have a graph for them, which is V with V, voltage measured in voltage, or potential difference measured in voltage, with current I in the unit of amperes. Now since that is a direct proportionality, we see that this graph actually passes from the origin and is most likely going to be a straight line. And the interesting bit of this would be that the gradient of this graph represents resistance. And I've discussed this technique before with you. How can we figure out this for any graph in physics, and how can you do that for everything? You see, we know that the gradient is y divided by x, or you can say change in y divided by change in x. We already know that, right? So simply consider the unit of y-axis, which is volt, and divide with the unit of x-axis, which is amperes, or simply I. And I realize that if I rearrange this equation, that is V equals to IR, I get voltage divided by current, that is going to be equal to R. So I can develop this common relationship over here, that V divided by I results in the value of resistance. So that is how we can figure out that the gradient of this graph refers to the resistance of that element that we are trying to measure the voltage across and the current of. So this resistance is actually defined as, in mathematical terms, it's defined as the ratio of potential difference to the current through an electric component. So what they're trying to say is that if by any chance, even if this is a conductor, for example, a simple piece of wire, if by any chance we connect in parallel a voltmeter to this wire, and in series we connect an ammeter to this wire, so and then we apply a battery, or we provide a battery. So if I had the reading of both of these components from the voltmeter and the ammeter, and if I were to divide these two readings, then I would find out the resistance of the wire. So basically what we're trying to say is, how much energy does it require for a certain amount of current to be pushed through a conductor that would make the resistance of that electronic component. So if less energy is required and that causes a high flow of current, that would naturally mean that the resistance of that component is very low. And if on the contrary, vice versa, we need a lot of energy, we need a lot of voltage, and that still is not good enough to cause a high flow of current, we will call that system or that component to be highly resistive. Do we understand this point?
Yeah.
Okay, all right. So this is how we visualize a resistance, a ratio of voltage to current, simply begging the question or simply asking the question, how much energy do we need to pump or do we need to provide to the electron so that they eventually move in some quantity from one point to another. So when we answer this question, we are actually dealing with, or we are actually thinking about resistance of that element. Anyways, we have two types of electronic components. The first one is an ohmic conductor or ohmic component. Now, ohmic conductor, as the name suggests, would follow Ohm's law very closely, and no matter what happens, they will not deviate from this ideal behavior. And that ideal behavior is that it is supposed to be a straight line from the origin. It's not going to get curved, it's not going to show nonlinear behavior anywhere in the graph or anywhere on the graph. Then we have non-ohmic conductors. By the way, in the real life, we don't have any ohmic conductors. They are just considered to be an ideal circumstance, or for the sake of discussion, it's an exaggerated situation so that we can at least discuss and understand what Ohm's law was. But it is followed by some components when the voltages are very low. When you're working with small voltages, components do follow Ohm's law. And we will get to that discussion later, how is that possible. Okay, so non-ohmic conductors, there are two possibilities. Their graph can twist and turn in two possible ways. Either it can be a curve like this, or either it can be a curve like this. It's possible that they don't even start from the origin as well, right? So it's likely in that regard as well. So, but very rare occasion that that electronic component or those circumstances are under very rare circumstances. For example, superconductors and so on and so forth. They would actually work on those circumstances. So over here we have a non-ohmic conductor, and in your course, in your syllabus, we have two non-ohmic conductors. The first one is the filament lamp, and the second one is the diode. Diode is a bit, you can say it's an advanced electronic component. So we're going to start with filament lamp and then we're going to move to diode, right? Alright, so an ohmic conductor in real life assumes that the resistance is constant no matter what you do with the voltage and current. But in non-ideal circumstances, what's actually happening at the atomic level is that when the current starts to flow through the structure, of course we know that there are fixed positive structures that actually make up the solid matter itself. So when the electrons start to flow in this way, they come in collision or they collide with these fixed positive charges. And as a result, when they collide, they slide past them, and this produces friction. And we know that friction produces heat. So the conclusion or the short form of this is very simple, that when actually current flows, the result of the current is that the conductor heats up. Now, it's like a chain reaction. When the conductor heats up thermally, the particles, these fixed positive charges, since it is made out of solid, their oscillation becomes stronger. They become more violent in their own oscillation. Now, when that happens, the chances of collision of an incoming electron with the fixed positive charge also increases. So first, if the path that was being obstructed by the positive charge was this much, now the obstructed path is almost this much because of the heat, because of the thermal energy. So this increased obstruction causes the electron to move even more slowly or collide even more frequently with these fixed positive charges when they're trying to move through the conductor. So what's going to happen after that? So as a result, when the chances of collision increases, the electron collides with those fixed positive charges more frequently, producing more friction, consequently producing more heat. And that heat again heats up the conductor itself, the particles become more violent, and so on and so forth. This is like a chain reaction that's never going to end, right? And as a result, the conductor starts heating itself up very rapidly, right?
And that's on the graph, it will be the one where it's sloping upwards. This
Uh,
example.
Not really. It will be the one that's sloping downwards, this one. The reason for that would be that once there will be a limit to this process, right? So there will come a time when no matter how much voltage you provide, no matter how much the speed of the electron there is, the heating is going to take over the system, and it's going to become so violent that the conductor will eventually melt rather than to increase or cause the flow of yes, you're right. This is the graph that we're actually looking for, because eventually there is going to come a time when the current is going to stop increasing after a certain limit. It would rather melt than to increase the value of current, right?
So what I'm trying to say is that there's an increase in gradient, so it doesn't follow Ohm's law because the resistance is increasing.
Yeah.
Okay.
Exactly. Since the resistance is changing, so it's not falling. That's why we're calling this as a non-ohmic conductor. But do we understand the philosophy behind the idea why current causes heating effect?
Yes.
Okay, all right. So this is the reason for the filament lamp, why filament lamps, or why the graph of filament lamp behaves the way it is. So we know that the filament lamp actually takes the advantage of the fact that we are generally trying to deliberately heat up the filament, so that when we do heat it up, it produces so much heat that it eventually turns into light. So that is why filament lamps today are actually obsolete. We don't consider them as an efficient source of lighting, because we are deliberately trying to heat it up so much that it starts emitting infrared and eventually visible light. So voltage and current graph of the filament lamp. Now, since they are red hot when they're operating, it's very likely that they have a very high resistance at that point. So the graph of that situation in filament lamp will look like this. Now be advised that this is voltage current. If I were to swap the axis like I and V, then the graph would actually change like this. So you have to be careful about this in the P1 MCQs, right? And even in P2 questions sometimes when he asks you to draw the graph. Now let's analyze the situation. I know that VI graph represents, or the gradient of the VI graph represents the gradient. And I can see that the gradient previously is this much, and then the gradient is increasing this much. So I can say that the resistance has increased. But how are we going to visualize this one? I can visualize the inverse of the gradient, but let's try to be more simplistic about this approach. So how are we going to justify this? I am giving more and more energy to the electron with increasing voltage so that it successfully or starts moving through the circuit with more current or more rapidly. But I don't see that change happening in the terms of current. I don't see that translating over here, do I? Can we see that? Right? So even though I'm increasing the voltage, the current is not increasing, which definitely means that the resistance at this point is so high, the temperature is so high, that even providing the electrons with more energy, that is being converted into heat rather than the translation of electric current itself, let's say. Do we understand this idea?
Yeah.
Okay. So that is what is happening with the filament lamp, right? So it's heating itself up, and there will come a time when the increase in voltage will not translate in increasing current. So this is the point where it fails the condition of Ohm's law, which is that they're both supposed to be proportional, right? Do we understand this idea? Okay.
So, like, at a certain point, the amount of resistance gets so high that it negates the effect that
Yeah.
the voltage will have on the current.
Yeah. So that is the trend of the filament lamp. We are supposed to be careful about this. We're supposed to relate heat, current, and the increase in resistance with each other. All right? Okay. So then we have the diode. We will get to this component much later. Okay? This is not the focus of this syllabus, so this is not the focus of this chapter at least. Diode is a part of our course, but much later in the series. Okay? So I'll get to that later. Just a bit of information about the diode. Diode is an electrical device that we use to make sure that the current flows only in one direction. So either it only flows on the right side or it only flows on the left side. It does not flow backwards. So we'll get to that later. Okay, so now what we've done is we have understood what is current, we've understood what is voltage, and now we have also discussed what is resistance and how we actually visualize it, right? And the one anomaly that we have, the most common one, is with the filament lamp, because it does not follow the Ohm's law. It will not, you can say, it's not following that equation. So I will consider that as a non-ohmic conductor. Okay, so the next aspect of our conversation would be resistivity. That is actually the next continuation of resistance. You will find these topics scattered in the book, but I'm just aligning them together in one smooth motion so that we can understand as much as possible. Okay, so resistivity. This is a mathematical value that gives you the idea about the type of material that you have used to make the wire. This is about the wire that we use for electrical connections, right? It is also for other concepts as well, but in your syllabus it's limited to the mechanical wire that we use for construction of a circuit. Now let's see that what does the resistance of any conductor depends on. So I understand that the length of the resistor or the length of the wire will control its resistance. So if the length is greater, the resistance offered by that piece of wire will be greater. And I also understand that thickness of the wire also has to do with this, also has to do with the fact of, or the effect of resistance. So how to visualize that? Why have I drawn this as inversely proportional? So if I have a smaller cross-sectional area, there is a higher chance of electrons colliding with a positive charge. If I have a wider area or a larger area, the electrons have wider space to go through them, and the chances of their collision with the respective positive charge of the solid structure are less. So if I increase the cross-sectional area, if I increase a thicker wire, the resistance of that wire will be less. This is exactly why you will see that heavy appliances, for example your air conditioner, your heater, your oven, juicer, blender, iron, all of these electrical appliances that are around you, they have thick wires because they are going to carry a large amount of current due to the powerful appliance. And the components that don't require so much power, their wires are generally thinner because we don't need such a low resistance for them because they're not carrying so much power. For example, if you look at the wire of the charger of your phone, that is much thinner than the wire that is connected with the air conditioner, right? So based on the application, we can specifically design what is the length and cross-sectional area for that application. All right, so if I combine both of these physical results or physical ideas, I get the equation that resistance is proportional to length over cross-sectional area, right? Now I want to convert this proportionality into an equality from simple mathematics, so I'll have to introduce a constant of proportionality for this equation. Again, L is the length of the conductor, how long the wire is, and A is the cross-sectional area, how thick the wire is, right? So in our case, this K is basically resistivity. This actually tells us the type of material. You see, copper, silver, aluminium, brass, all of these elements, all of these metals will have different values of resistivity. The unit is a bit interesting as well. So if I do the unit analysis for resistivity, I'll have to look at this one. By the way, the unit of resistance that we have done so far, the unit would be ohms. The unit of resistance is ohms, and we draw it like this as omega. The Latin symbol omega represents ohms, right? Okay, so if I come at this point and I replace the resistance units only, so what I'm going to get is ohms equals to K into length is meters and cross-sectional area is meter square. So I get 1 over meter and I'm taking that meter over there. So the unit of resistivity, which is rho, are equal to ohm meters. So this unit, not ohm per meters, but ohm meters. So in a way, this unit gives me the information about the fact that how much resistance we should experience for a certain length of wire. Not 1 meters, but for a certain length of wire. So just for the sake of understanding an example, I'm going to give you the values of resistivity of copper and resistivity of tungsten. Tungsten is the element that we use to make the filament lamp, and I told you that we deliberately take a high resistance wire for the filament lamp so that all of the electrical energy due to the high resistance can convert into heat, and due to so much heat, it will eventually convert into light, because that is how it's going to start glowing red. That is exactly how we have built or are using electric heaters, which are of course not a very efficient way of using electrical energy, but here we are, we have no other way. Okay, so the resistivity of copper is approximately 1.7 into 10 raised to the power minus 8 ohm meters. But for tungsten, that is highly resistive, it is approximately 100 into 10 raised to the power minus 4 ohm meters. Now notice that how conductive copper is, that its resistivity is minus 8, and how less conductive, or how much closer tungsten is to being a resistor or an insulator effectively, that it has such a high value, almost a difference of 10,000 between them, right? So if I were to find out the resistance of conductors made out of these two elements, even with same dimensions, let's say the length of both conductors is 1 meter, and let's make it 10 meters, and the cross-sectional area for both conductors is 2 meters square. If I were to find out the resistance for both, so the only difference in both of them, as R is equal to rho L over A, the length is same, the cross-sectional area is same, the only difference between them is the value of rho. And I can see that the value of overall resistance of tungsten is going to come out much higher than copper. So in short, looking at the value of resistivity, it helps me to identify what metal I'm working with, and it only helps us to bind this equation that we have in terms of mathematical constant, right? Do you understand up to this point what's resistivity?
Yeah, so it's resistivity itself is a mathematical value.
Yeah. And in terms of physics and in terms of physical reality, that gives you the idea as a designer, as an engineer, as a scientist, that what metal are you working with? And for example, in certain cases, the design requirement will be, let's say they want a 10 ohms resistor made out of tungsten. So it will be at your discretion what cross-section area you use, what length you use based on the application, right? So these are the formulas that they're going to use and you will use to design the respective resistor that is going to do that job for you, which has been asked or demanded from you, right? Okay, all right. So this is the chapter for current electricity. We have covered current, we have covered voltage, we have covered resistance, right? Now, last idea, that is the battery configuration. Battery configuration. You see, this single one or single piece is called a cell, and in most cases this will be 1.5 volts, unless or until stated by the examiner otherwise, right? So the longer line represents the positive terminal and the shorter line represents the negative terminal, and in our syllabus the conventional current always flows from the positive terminal to the negative terminal, right, after completing the circuit, of course. And cell or batteries are DC in nature, they provide direct current. Okay, so a single entity would be considered as a cell, but if I were to connect them in a few configuration like this one after the other, then now I will consider this as a battery, right? So I see that there are positive, negative, positive, negative, positive, negative, alternate polarities. This configuration in which the batteries are connected right now is called series, because the current has no alternate path, the current has to go through all the batteries. So in this case, the voltage adds up. Voltage adds up, right? So let's say if one cell was 1.5, then I have 3 cells. So the total voltage of this setup will be 1.5 multiplied by 3, simply 4.5 volts, right? And now let's try to connect the batteries in parallel. For example, There are 3 batteries connected as parallel because the current will now have an alternate choice to go through all these batteries. In this case, the voltage remains the same. Overall, the voltage remains the same. But then what's the benefit of connecting the batteries or cells like this? I will get to that later. So this is 1.5 volt, this is 1.5 volt, this is 1.5 volt. It's not possible that the examiner gives you a setup in which there is 1.5 and another battery is 2 volts and another battery is 3 volts. It's not going to be that way. All the batteries will be same and should be same to avoid any short circuits in the future. Okay, so what's the benefit of connecting this in parallel? There is a very major benefit, and that is what Tesla is doing right now. The only thing that Tesla is not sharing with anyone is not about their battery technology, it's not about their charging technology, it's about their battery configuration. We don't know how many cells are connected in series and how many cells are connected in parallel. Apparently that is what gives them the edge over the range that the vehicle travels to. And of course the engineers in other companies, Hyundai and Toyota and other people are also trying to figure out the battery configuration, but eventually they will get to that point. So series has its own advantage and parallel has its own. So what he has done is connected the battery in such a way that it provides the best of both worlds. We don't know that, he knows, he does. So let's look at the advantage. So the advantage is that it is going to last longer. So it is a long-lasting configuration. If you want anything to long last on battery, then you will be connecting that in parallel to multiple batteries. And the reason for that is that what batteries do is that they share the load with themselves. So let's say if an appliance requires 1.5 amperes of current, each battery will generally provide 1/3 of that demand as 0.5 amperes. As opposed to if this was only a single cell, then all the current would have to be given by the single battery, and that would drain it out more quickly, right? So, but the issue with parallel configuration is that the voltage is generally low. So you cannot run high-powered appliances. You cannot run high-powered motors or high-powered electric heaters. If you want a high-powered application, then you'll have to connect them in series, because when you connect them in series, the voltage adds up. More voltage means more joules per coulomb are available to the electron. It can run a high-powered appliance. But the issue with the series configuration is that it drains or it runs down quickly. So then again, how many batteries should be in series, how many should be in parallel? Even the battery of your laptop is connected in this way. Some cells are connected in parallel and some cells are connected in series. Wherever the voltage in your laptop, higher voltage is required, it will be getting that supply from the series configuration of that battery pack. Wherever long-lasting effects are required on lower voltage, that circuit is actually connected in parallel to that circuit, right? So that is how these are the qualities of series and parallel battery circuits, and we will design them accordingly, or we will design them or place them accordingly depending upon the application. But there is one question about the series configuration, and that is we have done what we've done so far is that alternate polarities, that plus minus come one after the other, and I can identify the number of cells very easily. So 1, 2, 3, 4. I have 4 cells connected in series, alternate polarities plus minus, plus minus, plus minus, plus minus. So I'll have 6.0 volts as the total EMF. But what if one of the cells was swapped by its terminal? So let's say I swap one of them. So we have 1 cell, 2 cell, 3 cell, and then the 4th one is actually swapped in this way. So what's happened over here is that we have plus, minus, plus, minus, plus, minus, minus, plus. So we need to realize that one of the cells is being swapped at this location. It is actually over here. So it's your choice. How students generally look at this is, there are 2 ways to look at this. What they do is they consider all the common battery pack on one side and all the other common battery pack on the other side. So they say that 4.5 volts are trying to push the current on this side, 1.5 volt is trying to push the current on that side, so the effective voltage is going to come out to 3 volts. That is fine, which is going to push the current in this way. Or you can say this battery pack effectively looks like that there are only 2 cells in the power in this bank which are trying to conduct the flow of current, right? The other perspective to look at this example is they simply cancel out the cells that are opposite to each other. So this is cell number 1, cell number 2, cell number 3, and cell number, sorry, not this way, but this way. So what they do is they cancel out the number of cells that are opposite to each other. So this cell is opposite to this one, so we cancel it out. What are we left with? We are left with 2 cells. So only 2 cells are good enough to cause the flow of electricity. So again, we are reaching, or we are getting to the same answer as before, right? So do we understand the complication with the series configuration? What type of question he may ask you in terms of a tricky question? Do we understand that?
Yeah.
Right? Okay.